Hello everybody and welcome to our first exercise in module 13-2. So this is our first randomized block design. Now you will probably notice a lot of similarities with this ANOVA, this analysis of variance, to the previous analysis of variances that we did in module 13-1. This is an extension to those what I will call basic, although I know they don't feel basic, but they're the simplest of the ANOVA. This is an extension to those ANOVAs in a very similar way as if you went through module 10, when we went through the transition from testing on 2 independent random samples. Then we went to the matched sample design. And so you may recall, as maybe it's been a little while, in that exercise, remember we had, say, 2 samples, A and B, and we had so many observations in each of those samples, and here we had sample mean A, sample mean B, and then we performed a test to see if we had evidence to show that there was a statistically significant difference between those 2 samples. Then we went into the matched sample and we started to talk there about accounting for different sources of variation. And I don't want to go through the whole thing again, but in a nutshell, what we had discussed was that because this experimental unit is different than this one, and this one is different from this one, and so on. So all of these experimental units, they're all different. Those that we have in treatment A or sample A are different from those that we had in sample B. That introduced that additional source of variation that in the matched sample design, we removed it by using a common experimental unit. So we had 1, 2, 3, 4, right? These were our experimental units. And then we gave both of those treatments to each experimental unit. And so we removed that source of variation. That gave us a more refined estimate of population sigma, and then we were more able to identify whether a difference here actually existed, because we had removed one source of noise, we had removed one source of uncertainty, of volatility in the data. Well, now we're doing that in an ANOVA framework. So again, in the basic ANOVAs, here we would have 3 treatments. We would have those 3 treatment means, and we were performing this test to see whether or not we had evidence to show a difference in at least one of those treatments. And so here we were taking that variation SST, which is the total variation in that data set. We split it up into that which was due to treatments and that which was due to error. Well, once more, now we can account for variation that exists between those experimental units. So just like we had for the matched sample, now we set this up as a set of what we call blocks. And I have 3 data points for each block. So we're giving each treatment to each of those blocks. And then we account for that source of variation. So we're now taking that out, SSBL and SSE. So by removing that source of noise, and when I say removing it, what I mean is that if we did not account for it, it just gets lumped into SSE. So now when we remove that source of variation, SSBL, and then we calculate that test statistic, which is exactly the same test statistic as for the completely randomized ANOVA, well, now by taking that source of variation out of the equation, MSE is smaller, the F statistic is larger, which means that if there is a difference, it's easier for us to now identify it because we've removed that one source of variation. And again, we end up with a more refined estimate of population sigma. Okay, so that's enough on that. I could talk for an hour, I'm sure, just on the kind of underlying theory of the randomized block. So let's just get into how to do this problem. You'll find it's very, very similar to the completely randomized ANOVA. There's just that one additional source of variation. Now here again, we're going to produce a full ANOVA table. So here we have treatment. Now we have block, that source of variation due to blocks, those differences across experimental units. And then we have our error, and then we have our total. Sums of squares, degrees of freedom, mean square, F, P, and what the heck, F alpha. So our ANOVA table gets a little bit bigger. But it doesn't really get any more complicated. That is to say, there's actually one part of this test, of this analysis, that becomes sufficiently complicated that in my course, we don't have a matrix algebra prerequisite. We don't have a linear algebra prerequisite. And that is a branch of mathematics that is now necessary to calculate SSE. So for my students, when I'm teaching this course, because we don't have that math prerequisite, for a randomized block experiment, I will always give my students either SSE or SST. So here I have that SST is 1304.73. And now with that piece of information, we can calculate SSTR, we can calculate SS blocks, and then once we have those three of the four, we can go back and figure out what SSE is without needing that linear algebra. We'll just calculate it based on this relationship. So if we have SST, we calculate SSTR, we'll calculate SSBL, well then I have three of the four pieces of that equation. We can solve for the fourth. Okay, so the underlying theory here is the same. We have a grand mean, and we have all of our treatment means, and we're going to calculate SSTR in exactly the same way as we've done in the previous ANOVAs. Here you can also see we have those block means. So these are the means across those blocks. And that is what we're going to use to calculate the source of variation due to differences across those blocks, across those experimental units. That calculation is also extremely similar to SSTR that we're going to do here and SSTR that we've done in the past. And then we already have SST, we'll obtain SSE, and the rest of this is exactly the same. It's an upper tail F test. Okay, and let's get into our problem. Everything company frequently relies on courier services to deliver sensitive documents between its regional offices. There are 3 courier companies available. Each one offers loyalty discounts, giving the incentive for customers to choose one carrier and stick with it. You decide to perform a test to determine if there are differences in delivery times between the 3 courier options. So we have 3 packages of equal size to each of the 5 regional offices. Each package is sent through one of the 3 carriers. Okay, so here's our randomized block. We have our regional offices. Those are our 5 experimental units. And I'm going to send 3 parcels to each of my regional offices, 1 through each of these 3 courier companies. Then we'll perform our test to see whether or not we have evidence to show that there's a difference in those delivery times. Okay, so SSTR, we'll start in that same spot. SSTR. So here we are looking at, remember when we did the completely randomized ANOVAs, we had a formula that looked something like this. NJ x bar minus grand mean squared, and we added those up across our treatments. And there was the number of observations multiplied by the difference between the sample mean and the grand mean. Well, now, due to how these tests are designed, we will always have the same number of observations in each of our samples, because I'm getting 3 data points from each of those experimental units. So if I have 5 experimental units, I'm going to have 5 observations in each of my samples. So I no longer need to have this inside of the summation, so I'm actually going to just rearrange this. And it comes out here, and now it's B for blocks rather than N for sample size. Change in notation, but exactly the same type of calculation. Okay, so here we have our 3 treatment means, and of course our grand mean. So 3148 minus 2997, oh, 2927. There we go. And the next one, 27.5. And the next one, 2882. And I'm just going to calculate all of those, and then I'm going to multiply through by 5. That's the number of blocks that we have. So let's do this, 3148 minus 2927 squared plus 27.5 minus 29.27 squared plus 2882 times 5, and that gives me 41.1. Okay, just like that. Pretty familiar calculation, right? Degrees of freedom, same as always, k minus 1. Here I have 3 treatments, so k minus 1 is 2. That mean squared is exactly the same. It's our sum of squares divided by our degrees of freedom, so that'll be 20.55. Next one, for blocks. Very similar. Here I'm now going to have x bar I, and where I just denotes the particular block rather than j, which denoted a particular treatment. Don't get hung up in the notation. It really doesn't matter as long as you understand the calculation that you're doing. There's that grand mean squared. We add those up across all of the blocks, and wouldn't you know it, we multiplied by k. Here we multiplied by 5, right? The number of blocks, because that's the number of observations in each of those treatments. Just as before, right, we had a calculation like this, we multiplied by nj, that was the number of observations in each of those treatments. Same thing here. We multiply through by k, because that's the number of observations in each of those block means. So now we're going to be going through, it's a little bit more time consuming. I've got these 5 block means. The grand mean is still the same. So starting off, 26.37 minus 29.27 squared plus, this is going to be a lot of back and forth, 46.33 minus 29.27 squared. Next one, 22.17 plus 2967 plus, I'm just going to squeeze in this last one, 21.8 minus 2927 squared. I love how my writing starts off big. I think I've got lots of room, and it gets smaller and smaller and smaller as I start to run out of room. And then all of that we multiply by k, which is 3, right? Because here I have 3 observations, and each of those block means. So I'm going to multiply that by 3. Okay, let's do this. 2637 squared plus, I'm just using brackets on this calculation, 46.33 minus 2927 squared plus 2217 minus 2927 squared plus 2967, and the very last one, 21.8. Multiply that by 3, and I have 12. Where am I here? 12, 1747. Okay, good. Now, our degrees of freedom for blocks, this one's a little bit different, but it's, again, nothing too complicated. This is going to be k, no, what am I thinking? This is just simply b minus 1. I just forgot for a split second. This is just b minus 1. So b, the number of blocks that we have, here I have 5 blocks. So b minus 1 is 5 minus 1 is 4. 1217.47 divided by 4. This mean square blocks, you know, we calculate it, but I'm not going to actually use it for anything. It's just part of a complete ANOVA table. Now I can calculate SSE, because again, here I've got all of these components. I know SST is 1304. SSTR is 41.1, SSBL is 1217.47. So I'm just going to use that to solve for for SSE. That's 1304.73 minus 1217.47 minus 41.1, and that gives me an error 46.16. Good. Degrees of freedom here, this is the one that's a little bit different. K minus 1 times B minus 1. So it's just the product of those two that are above. So that's going to be 8. Degrees of freedom total. Again, this one's always the same. NT minus 1. So when I come up here, I see I have 3 treatments, each one with 5 observations. So NT is equal to 14, right? That's 15 minus 1. So there's 14. And that's also 8 plus 4 plus 2, right? It's always the sum of the degrees of freedom above it. Okay, lastly, I still need my mean squared error. This is, again, the same calculation. I'm going to divide sum of squares error, 46.16, divided by 8. All these calculations, they're the same as what we did in the completely randomized ANOVAs in Module 13-1. All of those calculations are the same. Sums of squares divided by degrees of freedom, and those all give you these estimates of the variance. Remember those completely randomized designs? If the null was true, the sample means were all close to the grand mean, right? If the null is true, sample means are all in here, they're all close to the grand mean. If the alternative is true, Well, then we have a bunch of different populations, or at least one of them is different, right? Maybe this is the grand mean here. Maybe this is the grand mean. I'm doing this very fast because we've already gone through this in previous modules, right? Just to maybe refresh your memory from those previous discussions. If HA is true, remember we say the mean squared treatment is an inflated estimate of population sigma. It's inflated because the sample means are far apart. Well, the same methodology is what we're using here, except we're taking out that one piece of variation, that mean square block. So our test statistic is still MSTR over MSE. This is still an upper tail F-test. Is MSTR statistically significantly greater than MSE? If it is, well, that gives evidence in support of the alternative, which I'm just realizing I think we forgot to write. Yeah, well, we forgot to write it. Okay, well, it's the same. Null, we would say mu A is equal to mu B is equal to mu C. The alternative, it is what you think it is. At least one is different. Okay, so we're doing an F-test. If the alternative is true, MSTR is large relative to MSE. So let's look at this. Our F statistic is 20.55 divided by 577. 20.55 divided by 577. I have a test statistic of 356. What's next? F tables. Whew, it's the same, right? Same process. We're going to the F tables. Let's see, let's do this test at the 05 level of significance. I'm trying to get my small eraser. Here we go. So we're going to do this 05. Our degrees of freedom are variant of the F distribution. Here, mean squared treatment, I have 2 numerator. MSE, I have 8 denominator degrees of freedom. Okay, 2 and 8. So here's 2, here's 8. Here are my numbers of interest. Our test statistic was around 3.5, 356. Well, here's my critical value, 446. And our test statistic 3, it's kind of in between these two, right? So my p-value is between 0.05 and 0.1. So it's less than 0.1, greater than, squeeze this in, 0.05. So what do we find? Let's clean away some of this mess so we can draw some pictures. I need a bigger eraser. So here we have our distribution, some asymmetric F distribution. Way up in that upper tail. Get rid of all this nonsense. We have our critical value here was 4.46. As always, that defines our reject and our do not reject. We have a test statistic here, 356. You guys are getting tired of hearing me say all of these same things, right? This area here is 0.05, right? Because that was that critical value at 0.05, which means this area here, something greater than 0.05. So using our p-value rejection rule, using our critical value rejection rule, everything points to a do not reject. We have insufficient evidence here to show that any one of these three courier companies is different in terms of their delivery times. Whew, we did it. Lots of calculations, time consuming. But hopefully you see how similar these calculations are to previous ones that we've done. Now, we'll go through a couple of examples, and we'll also get into, in the next section, Module 13-3, the factorial ANOVA. And again, lots of similarities, few more complications, but we'll get there. Okay, thanks for watching. I hope this was helpful. Let's get into another example here shortly. Okay, thanks everybody. Bye-bye.